Hello, we are the RoboUtes. This is one of our robots. This is our submission for the RASC-AL Robo-Ops Midpoint review.
This robot's pretty good, but we've been making a lot of improvements. The drive system from last year's rovers continuously uses outreach events. We're using Xbox controller. We can have 5 or 6-year-old kids driving the rover around. Its strong points are its speed, its rugged and durable chassis, its awesome object traversal, and its unique spine suspension design. These combined attributes make the Mark IV a capable drive system.
We're taking the old stability and drivability of this old robot and moving forward and improving it with this new chassis. We're keeping the same basic design with the motors and the spine articulated system, but we've increased the amount of room that we have and the volume of the chassis for an onboard computer and an integrated rock box. We've got new space in the drive shaft for an encoder for a feedback-based drive system, so we're focusing on speed. And we're integrating a new shape in this chassis for rock deflection and making sure that we can really articulate over big obstacles.
Mark V communicates to mission control over AT&T's 4G LTE network. Due to recent changes in how AT&T assigns IP addresses to its users, we can no longer get a public static IP from an AT&T modem. The result of this is that at the beginning of a mission control is unaware of the location of the robot on the internet. To establish communication, the rover must first contact mission control, which has a known static IP, so known location on the internet. And then, once a pipeline is established, further data can be requested from the robot by each of the relevant terminals in mission control. So this year's onboard computer is significantly more powerful than it's been in previous years. That's so we can do more processing on board and minimize bandwidth required to talk back to mission control. Our computer this year is also directly managing all of the attached peripherals, including the arm, the drive system, camera systems, and whatnot. Whereas last year they were directly controlled through the router from mission control. Having higher throughput between our onboard computer and our peripherals allows us to get much more robust data, such as errors and diagnostic data, as well as to have more available bandwidth between the rover and mission control for sending telemetry data and rock positions, as well as video feeds. One major benefit of having this much power on board our robot is it allows us to have much more robust, much more intricate peripherals. Our sample acquisition system this year is an excellent example of that.
This is the Mark V manipulator. It uses linear actuators at the wrist, elbow, and shoulder to move in the vertical plane, and a gear motor turntable to rotate about its axis. This gives it a toroid-shaped workspace and allows multiple solutions to get to most positions.
Humerus up. Forearm out. Full extension.
An operator uses a custom graphical control interface to adjust the arm into a posture suitable for acquiring a sample and to close the end effector. The current control scheme is very rudimentary but surprisingly effective. As more intuitive controls and inverse kinematics are implemented, rock grass should become faster, easier, and more reliable. Future work will focus on bringing the turntable online, improving the controls and user interface, and hardening the electrical connections against the harsh realities of mobile operation.
Gently humerus up. Forearm out. Wrist forward. Humerus down. Hand open. Excellent work.